Okay, so we're recording now. Hopefully everyone's doing okay. The recording today, for whatever reason, I think the net connection in my area is not great. So the morning class was a little bit choppy and stuff like that. Hopefully it's not as bad. I've come up a little bit in my number of bars, as you can see, as I can see, but we'll see. So we'll have to deal with the technology. We're not quite where we need to be with this technology to go fully remote and online, but we'll try and make the best of it. So, any questions before we get started? We'll go over things. Now, I did say last time, go look back at anything else you have. So any other past problems, questions, confusions on what we've covered so far. Now, the central theme, what we've been dealing with, we started out with, kind of the idea, this course is essentially about functions and analytical technique. We introduced what a function was, and we talked about its domain and range. So that's a very important first step in our understanding of function, distinguishing what a domain is and finding it, and what a range is and finding it. So we looked at those in general. We also looked and did an aside at the beginning, which we will see and will be a common theme later on in the book, about something called an inverse of our function, that undoes our function. So we had something called an inverse function. And we use this notation that this is our function f of x. That's a new notation, which is essentially what we call y. The inverse function looks like f, not superscript -1, it's read as f inverse. It doesn't mean the reciprocal, it means the inverse function. And we looked briefly at how to find those. We're looking at classes of functions that require that later on throughout the text. But our central theme is domain and range. These are all the allowable x values and the possible y values that will come out. And you can see a lot of this when you use a technology to graph those functions. Then we started our journey over here on the first types of functions called algebraic functions. So there's different classes of functions. There's algebraic, and we looked at there's polynomials that we already did. And today we're going to introduce a limited set of what we call the radicals. Radicals are algebraic, as well as absolute value functions today. And then tomorrow, and maybe partly the next day, I have to check the schedule, we'll look at rational functions. Now, we're not going to define all their properties. And this is our first look at functions. We're looking at mainly the domain and the range. The range is the y value, so we're looking at the graphs to kind of give us an indication of that. And we're looking at different ways of finding these things, so domain and range. For example, to find the range for the polynomials, if you had a quadratic, we had to introduce a technique called completing the square. That was a technique we introduced to help us find the vertex of that parabola, and then some other information on that determined if it's going upwards or downwards, so we could distinguish the range there. For the domain for polynomials, they're defined all real numbers. So their natural domain is any real number, but in this case it was the range. What we're going to see today is for radicals, we're going to need another alternative for certain radicals, because radicals can be really complicated. We're only going to look at a very limited set of them. But for certain types, we're going to have to introduce how do we solve linear and nonlinear inequalities. That's mainly for their, if you will, domain. The range, we have to pretty much look at what the domain is, and you can look at a graph as well, and you can determine the range from that. Now, absolute values that you're going to see, that's relatively basic. Show the graph, we'll do that. Rationals that we'll not cover today, but tomorrow, probably on Wednesday a little bit, is a little more complicated, and we'll look at that as well. Now, we will come and revisit these functions again in the book. The first part of this is we're going to look at all the different types of functions and get their basic properties, very basic properties, and their domain and range. the set of allowable inputs and the set of all possible outputs. That's what we've been doing. So the book is also entitled Analysis, Techniques, and that's what these are. Completing the square, mainly nonlinear inequalities you'll see today. There's a technique we use for that. It's also an important tool moving forward. Okay, so that being said, does anyone have any questions on any of those homework problems and how to ascertain those two important aspects of the domain and range of all functions? And hopefully you're starting to get used to the function notation a little bit. We'll see more of that as we go on and progress further. So any questions on homework problems? We're all okay. Okay, so let's move on. So now we're going to go into these radicals, or radical functions. Now, radicals or roots are also can be thought of as inverse polynomial functions. Although, in general, radical functions can be way too complicated for us to even begin to consider. So this is our 2.3, is it? Let me see. Yeah, so 2.3 over here, radical function. Now, we in this course are only going to look at a very limited set of these types of functions. In general, it could look like something like this. Now, f of x could be some, function. I'll put it in some capital G of the variable x, as well as all various roots. You could have, the nth root of other functions called lowercase g of x, where that is, in this case, another function. In general, it could be extremely complicated. If you don't understand notation, that's okay. That's the best way. I put this in the book because it's even more complicated, but in general, it can be very complicated. We're looking at a subset of this, a very small subset of these radical functions. And what we want to look at is our f of x is some nth root of simply a polynomial function. So instead of anything, we'll just put a polynomial in here, because in general, we could look at some other functions, because this is under the umbrella of the algebraic. So it has to be a polynomial function to satisfy it. Although you could put absolute values and other things in there as well. But we even want to go into a smaller subset. So we take a subset of this subset, and our radicals are going to be the nth root of, something that is pretty much cubic polynomials or less. So cubic or less. 4th degree, 5th degree, we don't. And over here, we don't go beyond n for our index over here. It's, n is equal to a square root or a cube root. That's probably good enough. That's what we're going to be considering. So radicals in general can be extremely complicated because it can look wild and unwieldy. For example, let me show you just how bad it could look. If you're looking at a function, it could look something like this. There's one. It has a square root, a cube root, a negative exponent. It could look very unwieldy. We're not going to be looking at these. Those are way, way, way beyond the scope for us to be able to analyze in a very rational, reasonable way. Instead, we're going to be looking at some simplified versions. Okay, so let's take a look at some basic functions. And again, our emphasis is going to be on two different things. So our emphasis is going to be placed on finding the domain, or the natural domain, and the range. And let's start and build it up slowly. We're going to need a tool to analyze it. So we're going to start over here with, that and cubics or less. Let's start with a linear polynomial over here. So the first example we're going to look at is a linear polynomial in the argument. You know, ax plus b. That's a linear polynomial that will be under the radical symbol. Now, I also want to make some general statements here that's going to make our life a little bit easier. And it's kind of, it comes in this way. If we're looking for the domain of these functions, the domain is the set of all allowable inputs. So over here, we have to be careful if our index is an even number. That can restrict our domain. So the domain is dependent on the index of the radical. Meaning, if the index is odd, life is easy. It's all real numbers. Index is odd, then the domain is the set that, you know, x can be any real number. So if it's a cube root or a fifth root, that's okay. If the index is even, we have problems that we may have problems to contend with. So index is even, we have to analyze and find the domain. And that's where we're going to need some tools and techniques. And that's what we're going to focus on. So let's start with our linear polynomial of this form and find its domain. But this okay is going to be fine if it's a cube, you know, root or a fifth root. But we're going to look at square root. So let's see where it has some problems. This is the first problem now to analyze our function. So here's an example of a very basic polynomial function with a linear polynomial. Here's a radical. So let's use the square root. This is where we have problems. I'll say 2x minus 5. So that's a function, a very basic function. It's the square root, so it's an even index, because even though it's not written there, there's an index of 2. Remember, for the square root, we don't write the 2, even though that's what it is. So it's an even index. So we know one thing. Now, square roots have to have a positive or non-negative number under the radical. So here's my radical, that's the radicand. So for square roots, the radicand must or cannot be negative. So for square roots, the radicand cannot be negative. Why? Because that becomes, as we'll see later on, a complex number, and everything we're dealing with has to deal with real numbers when we graph it. We'll use complex numbers in a very interesting way later on when we introduce them in the textbook. So when we're looking for the domain for here, we must require, and this is we're going to use a linear inequality. So for the domain, we must solve a linear inequality, provided it's a linear polynomial there. So I would say that 2x minus 5, we're looking for when that is either positive or equal to 0. So it's either greater than or equal to 0. That's our domain. Any number x that satisfies that will qualify as a number in our domain. If it's negative, it will not. Okay, so we've learned how to solve those inequalities in previous algebra courses. Remember, an inequality is very similar to solving an equation with one caveat. If you ever multiply or divide by a negative number, you have to change the direction of the inequality. But this is easy enough to solve, so we turn around and let's solve that inequality. We have 2x minus 5 is greater than or equal to 0. What would I do? I'd add 5, just like I'm solving an equation to both sides. So this give me then 2x is greater than or equal to 5, and then I divide by the coefficient in front of the x, which is 2. Let clear that out. And I get then that x has to be greater than or equal to 5 halves. That's going to be my domain. As long as I pick x greater than 2.5 or greater, I'll be okay. If I pick x to be 1, and then 2 minus 5 would give me the square root of negative 3, which was a complex undefined over the real. It would not work. So how might we write this formally? So here's the formal way of doing it. The domain is a set of all elements x, and you could say such that if you want to put all the details, x is a real number. You can or cannot include that. And we require x has to be greater than or equal to 5 halves. That's my domain. Now for the range, you put in all the x values and see what will come out for the y values. But most of these, it's relatively simple. If I were to graph this, you can use your technology. I have, Desmos available. I'll do it in a second. But if I plug this into my technology, the square root of 2x minus 5 quantity, it would look like something like this. So again, now my domain are all the values that are above 2.5 or greater. That's everything, including 2.5 and to the right. That's my domain. And the function itself would look like that. So the range over here, remember, this is my domain axis. Yes, it always has to be positive. What you want under the radical has to be positive or 0. It can't be negative. So if I set it to be greater than, it's positive, or equal to 0, 0 is okay. Can't do it less than. We'll look at some other variations on this where I switch the signs over here, and you'll see how it looks another way. Doesn't always have to go this. But again, the domain is on the x value. That's where the domain is. And the range is all about the y values. Now you can see the output over here starts at 0 and includes 0 and goes to everything greater than 0. So for this one, the range over here, by looking at the graph, it's a set of all elements y such that, again, y is a real number. In addition, y has to be greater than or equal to 0. I will never get a negative quantity out of that radical. Domain of these values over here, from 2 halves on up, the range of those values there. Because that's the graph of my function. And again, you can either plug it into your PI calculator, or I'll just throw it into a Desmos calculator. So let me share that with you here. So here it is, and you just put in, my y is equal to, SQRT, and it will turn give me a square root. If I type SQRT, it will give me that. Now I get 2x minus 5, and there's the picture right over here. I can just move it around, and you can see if I kind of put it over here, just put the thing, it tells me 2.5, which is 5 halves. And you see my y value goes positive, and the x starts at 2.5 and goes all the way to the right. And it keeps going on and on and on forever and ever and ever. So we don't have to worry about that. That's a very simple way of seeing the domain and range of these types of functions over here. So use your technology. Technology is good to give you that sense of what's happening. Let me give you one to try for these and see how well you can do with this one. Now, these are just a limited set of radicals, and even they require a lot of work. So let me give you one to solve and see if you can find this domain and its range. Let me give you two, in fact. One is a simple one, and see if you get that, and then one is a little more. So try these. F of x is equal to the cube root of 1 minus 2x. With a little asterisk here. Think before you try and solve this. Then let's look at one that's much more complicated. Not much more, but significantly more. Here's another f of x. Is equal to the square root of 1 subtracting 2x. In each of those, see if you can find the domain and the range. As a hint for yourself, for the first one, plug that into your calculator or your technological device, such as a web thing, such as Desmos, and that should give you a sense. That one's much easier. I made a comment to that at the beginning of this lecture on the oddness or evenness of the index of the article. This is an easy one. This is where we have to do some analysis, because it's an even index, not an odd index. Put the answer here, and we'll go over it if you don't get it. Solving a basic linear inequality gives me this. Does anyone see this worked over here? So raise your hand if you want to see how I got my domain being that. Okay, so let's look at both of them and the distinguishing features. These are similar. The only difference is in this one, this is a cube root, and that's a square root. I can take the cube root of a negative number, so my domain can be any real number. But I can't take the square root of a negative number. That's why I have to restrict the set of x values so I do not make that the square root of a negative quantity. Now, if I plug in any value for x, I'll get any value out for y. I'll show you that on using Desmos. It's going to be my go-to thing. You can also show it, but I can show it much more quickly using Desmos and doing everything on the calculator. So here, let's take, and now sometimes you have to go with a root, so you can open up your little keypad over here and look at your functions over here. And I think I'm not sure if it's in the stats or it's in the miscellaneous. Right, yeah, here it is. This is the n root over here. So it's looking for the index, so it's cubed, so it's a cube root of 1 minus 2x. You can see that I can put in any value for x. It's all y value that comes out. And then what happens over here is, as I went out far enough, this would eventually go to, negative infinity to the right and positive infinity to the left. So in both cases, I get all real numbers. But let's put in the square root and see what happens there. So here I have y equal to square root of 1 minus 2x. And we're going to show how to solve this. Now you can kind of see this. It actually starts here, so there's a value of 0.5 for x, which is that, and it's to the left, so it's less than or equal to 0.5. Well, how do I get that algebraically? I can see how I get that graphically, and at the same time you can see the y values in the other one, so in this one, starts out at 0.5 and then goes up to positive infinity. But how do I do that algebraically? Let me go back to this and approach this algebraically. So first off, hopefully everyone sees, if it's a cube root or a fifth root, it's always the same, all real numbers. Only problem occurs when I have a square root or a fourth root or a sixth root. In this course, you just pretty much see square roots. Very, very rarely will you see a fourth root, but for the most part, it's all going to be square roots. But how do I find that specifically? So what do? Just like in the previous one, I take what's the radicand, under the radical, that's the radicand, and I want to make that non-negative. It has to be always positive. Whatever's under there, I want to make it positive. So let's go and solve this. So what might I do? I might subtract 1 from both sides. I'll subtract 1. This gives me a negative 2x is greater than or equal to a negative 1. But now I'm going to divide both sides by a negative. But whenever I divide an inequality by a negative, I have to change the direction of the inequality. So I start negative 2x and negative 1. And if I divide this side here by a negative 2, I have to change greater than or equal to less than or equal to. That has to occur at that moment. Now, you say, why is that? To make everything make sense. This is the reason why. If you didn't do it, it's kind of due to the properties of numbers. Because we know that, negative 3 is less than a negative 1. It's to the left of negative 1. Now, if I multiplied both sides, or divided both sides by, say, negative 1, I'll divide this by a negative, and if I didn't leave, or didn't change the inequality, without changing it, I get 3 is less than 1, a contradiction. The only way to rectify that contradiction is to switch the direction of the inequality, and then it will make sense. This is why you have to change that direction. Otherwise, you don't get a contradictory statement. And when you do that, you then get x is less than or equal to 1/2. What I have here, which is also born by the graph that we just saw. So we looked at the graph. Over here, too, there's 1 right at 1/2, kind of moved that way. So my domain now is all these values from 0.5, including, and everything to the right of that. The range are all the y values, so y goes from here all the way up to plus infinity. Okay, so that's a linear expression under the radicand. Let's take a look at a slightly more complicated one. Question. If you multiply or divide by a negative, you have to change the direction of the inequality. Let me see specifically what you said. It stays in my window. No, if you multiply or divide by a negative, you have to change it. It's just as I said up there. Otherwise, it will not preserve the same sense. Okay. I have to quickly look at the chat. So now we see how to find the domain and the range of a very basic square root and cube root function. Square root, more work. There can't be negative under the radical symbol. Cube root, it's relatively easy. All real numbers for both. Okay, so now let's kind of make it a little more complicated, slightly more complicated example. Something that's similar to what you see in the textbook. so you can have reference to it. So now let's say I have this example. So here's my function. It's a square root, so I know I'm going to have problems. I have difficulties I have to worry about. And I have x squared minus 3x subtracting 18. This is no longer linear. Now we're dealing with, instead of linear polynomials, we're dealing with quadratics. So quadratic under the radical or the square root symbol in this case. If it is a square root, again, we have to make sure that that is always positive. It turns out that there are 3 ways in which we can solve this problem. One of them is graphical or analytical or algebraic. There are 3 ways to address the problem of finding the domain. Address the domain problem. The first way is graphical, and I'll show you that. The second way is an algebraic approach to solving a nonlinear inequality approach involving function evaluations. The third way is very similar to this, but it's a little easier. It's a little bookkeeping approach, and it's also an algebraic approach. Involving factor evaluation. And I'll show you each of them, and then you'll see how it will be duplicated. Because again, this is what I want to solve. Just like all the other problems, I'm approaching it, and I have to make sure that whatever is under the square root, that's x squared minus 3x minus 18, it has to be non-negative. So that's what I'm looking at solving. That's my focus. So that's a parabola. You can see it's a parabola that opens up. Let's graph this. So let's take a look at the graphical analysis of that and see if we can find the domain. Now, I'm going to want you to be able to do these other techniques. It's 1 and 3, I think, are definitely techniques I'd like you to be able to master. 1 is simple. We'll go back to our Desmos again. So let me just kind of get rid of that. Come over here and put the square root. SQRT of x squared minus 3x minus 18. You can see some strange looking results come out of this. But now you can kind of see this value of 6 over here. In this case, x has to be greater than or equal to 6. It goes to the right. I can't put the value of 0, 2, 4 in there, but I can go to the left from -3 also to the left. So if I look at the graphical approach to solving this, I'm going to go to the board now and take a look at that. So here, if I go to the approach, I can see by plugging in what's under the radical symbol, or what we call the radicand, I get something that looks like this. There's 6. There's -3. My function looks like this. From this, we can ascertain, hopefully you can kind of see this, the x value has to be to the left of -3. So over here, it's all these values. This is that. That and to the left. So here, x is less than or equal to a -3. That's part of the domain. It's an allowable value for x. Or, 6 over here and go to the right. So x is greater than or equal to 6. So if I want to analyze the domain and range of that function, here's a graphical way of doing it. Gives me a nice picture of what's happening. I can do the following. I can start with the domain. So for this domain, well, elements x is a real number, and it has two conditions. So x is less than or equal to a -3, or x greater than or equal to a +6. Two conditions. It's an or, either or. If it satisfies that, either one of those conditions, it's in the domain. Now the range is a little bit easier, as you can see. For this, the picture tells us what the range is. That's all my y values. You know, y again is any real number, except there's a restriction on y. I don't have my function beneath the x-axis. So it does give me y equal to 0, but it's also, everything is above the x-axis. So y has to be strictly greater than or equal to 0. Now you may ask the question, is that the same range for all of them? Predominantly, unless, for example, I put a negative out front and then it would flip down and it would be less than or equal to 0. So it's a different sign out front. If that was a negative of that square root, that the range would then flip. Well, and would be, both would be required. The AND operation says it would have to satisfy both, and you can't satisfy both of these at the same time. When you write an AND, that means both must be satisfied. So, meaning it would have to be in this interval and that interval, which is impossible. It has to be either or, either or. The AND operation says this has to be true and that must be true for that to be accepted domain value. So if I put n there, it would exclude everything. There's no number that's in this interval and that interval at the same time. That's what the n means. Both have to be true. The or says it's either this is true or that is true. If either or of those are true, you're okay. And it satisfies that inequality there in that way. Good questions. Keep asking those questions as we go along here. So graphically, it's relatively easy. And if you again get fixated, domain are all the allowable x values, the range of all the possible y values. So if I wanted to get y equal to 0, I could either put in a -3 in here or a +6, and I get the square root of 0, which would give me 0 in both those cases. Any other number in that range will just put me out. If I pick anything in here, for example, if I plug in 0, let's just kind of verify this. If I plug in 0, I would get f of 0 is the square root of 0 squared minus 3 times 0 minus 18, which gives me the square root of -18, because those are all gone. And that is not a real number, so not a real number. So that's why it is not displayed in your Desmos kit. I'm trying to avoid taking the square root of the negative number, and that's what happens here. I let the calculator do the work. Okay, let's take a look at the algebraic approach for that, the two of them. So that's our graphical. Now we should get the same exact answer, and I want you to be able to do this because we're going to have to solve nonlinear inequalities. So let's do the same thing right now, using the algebraic approach. Actually, we'll use our graph to find the range, though, because that's the easiest way to find the range. You can reason through it, but some students have a little bit of difficulty with that. As long as you find the proper range, I'm okay. So let's take a look at our first and algebraic approach. And we are, solving a nonlinear inequality. X squared minus 3x minus 18 has to be greater than or equal to 0. Now, there's two different algebraic approaches, but they both require that the first step, if possible, and most of these we're going to set it up that way to give you that experience, is to factor, if possible. So factor that expression. So basic factoring that you did in your prior algebra courses, and this will factor into x minus 6 times x plus 3. What you want to get out of these factors, so after you factors, and the second thing is find what we call the critical points, where that goes to 0. So find what we call the critical points, or where each factor gives a 0. So I solved each of those separately, kind of doing it over here. So I said that x minus 6 is 0, adding 6 to both sides says x is equal to 6. And then the other one, I also solved x plus 3 is equal to 0, or x is equal to a negative 3. Those are my two critical points. Well, this is starting to go out on me. I need a new, an earlier morning class. I need some more ink. Otherwise, that will fade out too much. Okay, so once we have those critical points, what's our next step? Well, the first technique we'll show is a simple function evaluation. Okay. So the first of these algebraic approaches, I'll put approach is the following. And this deals with what we call function evaluations. So we have these two critical points specified on the x-axis. Here we have negative 3, and here we have positive 6. Now, remember the x is our domain. We want to fill in what's acceptable and what's not. So what we could arbitrarily do, we know it's going to behave differently as we cross those. I could evaluate this quadratic in any one of those intervals. So let's do that. So this is going to involve now function evaluation. So I'll pick a point, say right here. That's an easy point, which is 0. Pick a point over here, which is negative 4. And I'll pick a point over here, which is a positive 7. Those are arbitrary. Any point on the interval will do it. It's a negative 5. I could take negative 3.1 if I wanted to, a positive 6.1. I just arbitrarily picked those evaluations, meaning I'm going to evaluate now f at, I'm going to evaluate this polynomial, so when x is equal to a negative 4. So that means I got to plug it in, and I get negative 4 quantity squared minus 3 times a negative 4 minus 18. All I'm concerned about is its sign. Is it positive or negative? That's all I'm concerned. This is 16 plus 12 minus 18. And you can see that gives me 28. So in this case, I get 10. Positive 10, which is greater than 0. So that's OK. That means anything in this interval over here is part of my domain. I verified that I get a positive under the square root. Put in 0. So now evaluate at x is equal to 0. So what do I get? I get 0 squared minus 3 times 0 minus 18. That gives me negative 18, which is not less than 0. So in this interval over here, I omit all those values. Now you can try any number. It will work out. Those critical points, when they go to 0, this will work. Then I pick the last case over here, x is equal to 7, plug that in, so I get 7 squared minus 3 times 7 minus 18. You get 49 minus 21 minus 18, and that gives me 49 minus 39, so that gives me a positive 10. And again, I'm positive, so anything in this interval will work. And then to write my domain, I can see what's happening here. Domain is a set of all elements x, such that x, I could say it's a real number. Let me skip that. If x is less than or equal to -3, or x is greater than or equal to a positive 6. That's using function evaluations to do that. That's one of the algebraic approaches. And this just kind of shows. Now you can pick any number over here, it doesn't matter. Let's look at the other algebraic approach. This is the one that can be useful for looking at much more complicated inequalities. This isn't, so bad since it's a quadratic, but later on in the course you might look at inequalities that might be cubics or quartics and other things happening. And what do you do? So let's take a look at that. That's the second, and that is my factor evaluations. And here's the second algebraic approach, and this deals with factor evaluation. We have our polynomial, our quadratic factored into this. And we're looking at each of those factors. So we have the x minus 3 factor, we have the x plus 6 factor. And what I'm going to do is I'm going to look again like the same thing over here. I do it in my number line. And I'm going to put in my critical point. So I still find the critical point. I put in -3 and I put in positive 6. And here's my domain or my x-axis over here. Then what I'm going to do is I'm going to evaluate each of those individual factors for, x, a value to the left of -3. So for example, if I put, number to the left of -3, whoop, keep me away. This is positive. This is x plus 3. Keep me away. Talking and writing at the same time. X minus 6. Plus 3 minus. The only way I'll get the -3 x to work out. I have to switch over there. And I have it evaluated, but I just miswrote it over here. Okay, so now we pick anything to the left of -3, such as -4. Well, -4 plus 3 means in range, that x plus 3 will always be negative. It's always going to be negative. Then when I go into this range, such as 0 plus 3 becomes positive. For any value of x in range, that factor is positive. Continuous over here. It's still positive over here. Pick 7. 7 plus 3 is 10. It's positive. Now let's move to the x minus 6. Well, pick anything to the left of -3, such as -4. Pick, say, 0 in this interval, or 5. 5 minus 6, it's all negative in this interval. Then it hits its critical value, and then it becomes positive. Okay, this, however, is a product of those two. So what I'm looking at now is the first expression times the second expression. So here I'm going to look at x plus 3 times x minus 6. Well, in this interval, I have a negative times a negative, so that's a negative times a negative, so that is positive. In this interval, I have a positive for the first factor and negative for the second factor, so when I multiply a positive number times a negative number, this is negative. And here I multiply two positives together, and I get positive. I have to require that this is either positive, so it's all the positive values over here, the positive values, as well as 0. I shaded in 0. That will then directly gives me my domain. Here it is. I'm going from minus infinity up to and including -3. That's that one. Union over here, +6 up to +infinity. And I include, with the brackets there, including the endpoint here. Infinity plus or minus infinity is never included. You never have a bracket around it because it's kind of limiting. But that's how you kind of look at it this way. And instead of evaluating functions, you're just evaluating all linear factors. And they're easy. Plug in a number to the left. Any number, it'll tell you the sign. So this times that is positive. Yep, choose arbitrary numbers to the left of -3, arbitrary numbers between -3 and 6, and an arbitrary number greater than 6. Pick any number you want, and it's easy to do the evaluation. And that will give me the same solution over here, meaning x is less than or equal to -3, or x is greater than or equal to +6. So that's evaluating factors. And now this is a very common and very useful one to analyze. So you have 3 different techniques: graphical, the function evaluation, and then the factor evaluation. But both of the algebraic, you have to find those critical points first. And also, you can use the graphical to kind of make sure you understand what's happening with the algebraic. You should be able to use both graphical and algebraic techniques on anything. The algebra will come in handy. Okay. We'll give you something to try in the homework. We'll see. Yes, Ashley, you have a question?
Yes, before you erase all that, wait. Before you erase all that, where, I'm sorry, I just froze for a second. Why did you separate the two parts before you did the whole thing together? Like,
it's just easy. It's an easier divide and conquer strategy. Meaning, if I just look at that piece and I look at that piece, then I can multiply them in the end and put them together. The reason I did this is because it's easier. If I'm just looking at x plus 3, it's a lot easier to find the sign of that if I put x equal to -4. -4 plus 3 would give me a negative quantity. This is easy. It's kind of like divide this complicated structure up. That becomes negative, that becomes negative. So this is a negative number, that's a negative number, so I have a negative number times the negative number gives me a positive number.
oh, I see. Okay, thank you.
Later on, you'll look at inequalities that something like this. That's the reason we're doing it, because later on, you're going to see inequalities that might look like this. And then maybe it's going to go negative. Look at that. So more factors over here, it's easier to break them down separately, and you can do it quickly later on. This is what you'll see. So I've kind of given you a see for that simplified way. But these 3 techniques give you the same result in the end. The picture into the domain. For the range, the easiest way is to just plug that in, and we saw the range went from 0 to infinity. I plug it into a calculator or graphing device. Okay, but now sometimes you have to look, and you have a quadratic, and it doesn't factor. So sometimes, don't be confused. Plug into your calculator or onto your computer screen, because you might have this as an example. Here's a simple example. Another example, f of x, it's a square root, so I'm already, my hair in the back of my neck is up, standing up to the square root, could be a problem. But what if I have this? X squared plus 4. Well, you might notice over here that, okay, it can be any real number, because this is never, so x squared plus 4 is never negative, no matter what. I put a negative value for x, I square it, I get positive, I add it to 4. Can't get a negative value out of that. So we can, just by looking at this, argue that the domain, in this case, is the set of, x, let's set x is any real number. We'll throw it into a graph and analyze it. This is a little bit different. This can never be negative under the radical. Now the range is a little more complicated. You may recognize that the smallest value this can take is when x is 0. So when x is 0, I get my smallest value, which is the y value, which is the square root of 4. So that tells me y has to be, square root of 4 is 2, it has to be greater than or equal to 2. Now you may not have recognized this, but that's okay because we could use our decimals or our calculators. So let's plug it in and see what that graph of that function looks like over here in this regard. So I'm going to get rid of this and put in x squared plus 4. Look what we have over here. My domain, I can put in any x value. Any x value down here will give me y value. The range on the y values. So if you're looking at this graph, the range is y value. Over here. To repeat what I'm saying, for every x value, I can find a y value. So that means all the entire x-axis is a domain. There's always an associated y. Looked at some of the other ones, that was not always the case. For example, we had some that looked like this. And over here, yes, for all these, I can find an associated y. But over here, there's no y value. No y value over here. So that's not part of the domain. Only this, like we looked at the previous example, that's where the domain was. That's the natural domain. Because what happened over here with the other one, I ended up with a negative under the square root. And that is a complex number, and we're not going to be dealing with that just yet. But as long as I have my function is everywhere I want it above the x-axis or beneath the x-axis, meaning there's a corresponding y for any x I choose, then that x is in the domain. Now the the range is just all the y values. So y will never, ever be beneath 2. The y has to be greater than 2, and that's my range. Okay, so